All right. How are you guys doing? All right. So I want to thank again Brink and NEA and company for sponsoring this, and thank Andrew for the very chill rainy day intro. I thought it was really like in vibe with like what's going on outside. I just had a lot of coffee, so I'm gonna be a little less chill, but hopefully like as engaging. I'm also going to time myself so I don't go over time. So again, my name is Ajay Kulkarni, co-founder, CEO of Timescale, and I'm here to talk about why IoT and the Internet of Things, as we think about it, doesn't really exist, but how it'll still reshape our business. Timescale, we're an open source time series database. Who here is familiar with the world of open source? Perfect. And the time series data. Awesome. Great. Yeah, great crowd. We're powered by Postgres, and I know some of you use Postgres as well, which is awesome. Put another way, what we do is we empower organizations to analyze the past, understand the present, and predict the future. Those organizations include some of the ones that are listed below, who are all today using Timescale in production. We launched a little less than 18 months ago, and in that short period of time have seen quite a bit of growth. We just passed 1 million downloads, which we announced last week. Yeah, who said that? Thank you. and we've raised $16 million from some top investors, including Peter Fenton from Benchmark, Forrest Basket from NEA, as Andrew mentioned, the folks at Two Sigma Ventures who are here in New York, and a group of some awesome angels. And TechCrunch also wrote a really nice piece about us earlier this year. Also, last week we announced that Timescale is now 1.0. Big blog post. If you want to read about it, it's on our website, blog.timescale.com. But what I'm here to really talk about is IoT, but really like 3 ways to embrace this next wave of computing. And the first insight, kind of the first way, is kind of a heretical thought. And it says the thoughts in the title is that actually to recognize there is no IoT, but your business is changing. And I'm going to explain what that means in a minute. But at a high level, when I say the word IoT, who here, thinks of something like new and shiny and exciting? Like 2 people, that's crazy. Okay, and who here thinks of like something that's maybe a little tired and hyped out and like where is it? Yeah, a few people. And I think that's the interesting thing about IoT is the question I want to start off with is like, where is this shiny AI connected future of things that we were promised, right? And I feel like the past few years there's been a lot of talk and thought pieces about how our world is changing, but it really hasn't changed that much, like not yet. And I think there are a couple of reasons why. I think one reason is like, to be fair, sometimes exponential growth, it takes time. And in the beginning, as things are changing, it's hard to notice that they're changing. But after a while, once you hit the inflection point, it really starts changing very quickly. So that's definitely happening. But I think there's something else that's kind of deeper happening. And to kind of understand that, I thought I'd walk through history. The way we think about IoT or this next wave of computing is we think of it as a next wave of computing. When we think of the computing industry, we think about first the mainframes that came about in the 50s, and then the personal computers and laptops in the 80s and 90s, and then in the 2000s, the rise of the smartphone. And with each wave, you end up getting these. The machines get smaller and smaller, but they also became more and more powerful, and they became more prolific. And I think what's happening now is, computing is becoming so small and so ubiquitous that it's getting embedded in everything. But there's something kind of, I think, unique about this next wave. If you think about, say, personal computers, they all essentially ran the same operating system, like Windows, right? And all the PCs kind of look the same. And if you remember back in the 80s, we called them clones. We called them PC clones, right? Think of the smartphones. We've essentially coalesced to 2 operating systems, iOS and Android. And in fact, even though they're different types of phones, at least on the Android side, because of a need for a consistent set of hardware APIs, the phones themselves are also kind of standardized around what kind of features like a phone would have. IoT is actually very different, and it's different because all the things are different. So I actually want to kind of pose a question is like, if you look at these 4 examples, a Nest thermostat, something in predictive maintenance and maybe manufacturing, an autonomous vehicle, and a wind turbine, like, are these really the same? And at first glance, like, they don't look the same. And, what are different ways where, you might think that they're different? What's that? Moving versus not moving. Totally. Love it. What else? How they collect data. Say more. Like the network connection?
Their source data.
Source data. Yep, perfect. You're in the manufacturing world. Is your business the same as like the Nest thermostat business?
Well, what's funny is we found a lot of the sensors are the same. It's just about how you collect the data.
Yep.
What you do with the action.
What do you do with the? Yep. What do you do with the action? Love it. Yep.
Robots are taking our job.
Robots are not almost. Almost. I'm getting there though. We'll get there. Here's what I find interesting is that these are, they may share some hardware components. I think it's a totally valid point. And I think there is this, economies of scale as we come down the cost curve, which I think was initiated by smartphones, which has led to hardware getting cheaper and cheaper. But if you look at these 4 devices, they essentially have very different constraints. They have different constraints in terms of, if they're moving or not moving, constraints in terms of power availability, are they plugged in or on the battery, bandwidth access, are they on a Wi-Fi or are they on like a cellular or Zigbee, computational power, and also the budget that you're building towards. And I thought I'd actually walk through a few different examples. And I actually find, for example, the first two very interesting, because an Amazon Echo, it's plugged in, it's on your Wi-Fi, it's a mini computer, or it is a computer, but you're selling to the consumers as a small budget, so you're constrained by budget. But look at a vibration sensor in a factory. I'm not sure that's what you guys are doing, but vibration sensors, you may or may not have power. You might be battery operated. You may or may not have bandwidth access. Maybe you're on a Wi-Fi or not. But if you solve the right problem, there's actually a budget you can tap into. And again, if you look at these next two in agriculture and connected light bulb, they're almost exact opposites, right? In agriculture, you're out in the fields, so you probably battery operate on a cell signal, but you actually may have some power, but you may have actually a significant budget to tap into. With a light bulb, you're selling to the consumer, so it's really disposable items. There's no budget. There's tiny devices, so no computational power, but it's actually plugged into a socket. So you actually have, actual power, and you may be on the Wi-Fi. In the smart street lights, I think is kind of this weird unicorn example that doesn't have any constraints, but I guess you have to sell to a city, so maybe that's the constraint that you have to think about. So this is one way that this world is different, and I think it's challenging to put this all under one umbrella. Another way is, and I thought maybe this is what you're getting to, is because of different constraints, you end up with different topologies on how the data is collected and transmitted upstream. I think some cases, like an Amazon Echo, you might be on the Wi-Fi or just plugged into Ethernet. It's direct to the cloud. In a factory, I'm not sure you guys are collecting data. How are you doing it?
Most factories already have a historian in place.
Yep. Right. So how does the sensor connect to the historian? You're probably through some last mile protocol like a Modbus or something. To the PLC. Totally. There's a last mile protocol that you wouldn't have in the home, right? Yeah, right. Totally, right. So there you have like this like almost gateway like setup where I'd put maybe the historian here as the gateway, and in some cases, and this is less common, but in remote installations like oil and gas, you might actually see like a multi-hop network where the packets are kind of go node to node to node until they get to a node that's actually plugged in. So again, like this is a very different world than say this world where everything is on Wi-Fi and cellular, or the desktop PC world where you're either plugged into Ethernet or on Wi-Fi. So insight number one is, if you think about all these constraints, like there actually is no one IoT. There's no singular IoT. And so it's hard to say, hey, I want to embed IoT in my company, because what does that mean, right? It depends if your company's in the factory business or in maybe a moving vehicle business, right? But your business is changing, and that's what we're going to get to. So insight number one, there is no IoT, but your business is changing. Insight two is one way that it's changing. It's this new idea called the hardware as a service business model. Who's heard of this business model? A few people. Cool. Here's an interesting graph. This is looking at the stock performance of Fitbit and GoPro over the past 3 years. And looking at this graph, I want to ask the audience, how many people here have a Fitbit or a GoPro that they've purchased in the past few years? Only 2 people? Really? Wow, 3? 4? How many people here are still wearing their Fitbit? Like 1 person, right? And so here's what's interesting is like what happened here? Like these were IoT businesses, right? Like Fitbit was like the IoT like unicorn, and GoPro, people were talking about how it's going to be the next wave of something, I don't know, next wave of media. But the stock prices collapsed, and there's a complicated story here. But one thing that happened is these businesses were in the hardware business where they're just selling a one-time transaction, and they were stuck in this loop of every holiday season trying to convince you to replace your Fitbit. And after a while, either you're happy with the one you have, or you're not using it, so you don't need a second one. That's where hardware as a service comes in. So what is hardware as a service? It's this idea that has its roots in SaaS, software as a service, obviously. It's a business model where you're not just selling hardware, but you're selling packages. Right? You're selling packages that include hardware, software, and maintenance for a recurring fee. And in particular, the customers pay for the services, not just the thing, right? And number three is the contracts themselves include, because you're paying for a service, they include a service level agreement, an SLA. Does this resonate with people? I'm actually going to walk through a few examples that kind of, I think, better illustrate what this means. The first example is right here in New York, a City Bike. I think this actually is a great hardware as a service example. How many people here are a City Bike user? Great, yeah, awesome. Where it's solving the problem where either I don't have a bike or I don't feel like bringing my bike out and trying to find a parking spot. And what City Bike offers is as a bike as a service, and they have an SLA that roughly says when you need one, we'll have one available, and when you need a docking station, we'll have one available. And usually that works. I have a second example that I think is actually an even bigger company, but similar, which is Uber. And I think Uber is really interesting because I think most people don't think of it as an IoT company. I think we probably have a long debate about this, whether it's an IoT or not. I used to think it was an IoT, but then I realized the fact that the connectivity is provided by a phone was irrelevant, that it actually was a connected car. And when you actually hire an Uber, when you get a request an Uber, you're not just requesting a car, you're actually paying for transportation as a service. And again, what Uber is doing, especially in urban environments, is reducing the need to have, not just, a taxi, but a car in general to get from point A to point B. And in fact, let me get you a second. And in fact, I think the city of New York found that Uber had reduced subway ridership since it was launched, which I think is actually kind of nuts. A city like New York. Yeah, question.
You're pressing your phone to make another human move.
With Uber, you're pressing it.
Yeah. With my phone, I can make you come here.
Right. But I think what's
finger.
I think what's interesting.
With my finger, I can make you dance.
I think what's interesting is you're right. Although I think what's even more interesting, and this is obviously where Uber is going, is the human is just a temporary solution. You're just requesting a car, and because the car right now can't come to you on its own, a human is driving it. But in 10 years or 15, I don't know, what do people think? I think that'll change. But yeah, totally. And I like that energy too. Thank you. So the third example is actually even bigger than Uber, and it's actually a business that's generating, I think they're up to like $18 billion in revenue. Any thoughts and guesses on what that might be? Huh? Close? I'll give you a clue. They also sell books. It's Amazon. So here's what's interesting is Amazon, most people think of Amazon as like a SaaS business, right? Because they're one of the first kind of credit card pay-as-you-go services. But what they're actually offering is a hardware, right? They're offering you servers and racks and data centers and storage and compute as a service. And I think what's interesting is they started a long time ago before I think even hardware as a service was even coined. But this whole idea of even cloud computing, which is often used as, I think, the canonical example for SaaS, is really an example for hardware as a service, because what you're really paying for is the hardware without needing to maintain it. Does anyone disagree with that? I'm not sure that's controversial. You disagree with that. Why?
I think you're paying to ignore the idea of hardware, and AWS for the most part is.
I agree. But I think the same thing with Uber, right?
Different. You can't ignore that you're in a car.
Yeah.
in Uber, but you can ignore that servers exist and you're on Amazon.
We can debate this one. Totally cool. But here's what's interesting about these three models is hardware as a service. I think these things exist and they're popular for like quite a few reasons. So number one, like there are advantages to the customer, right? The first advantage is, hardware is often depreciating, but you can lease it. You can lease it. You don't have to actually take this upfront investment on a thing that's going to depreciate over time, right? And as a result, you're converting this massive upfront capex to an operating expense, which number one is easier to budget, but it's also easier to value because you can say, well, I'm paying like $20 for this car ride, is it worth it? Or in the case of Amazon, I'm paying $200 a month for, or that's probably cheap, like two grand a month for this server. Am I generating that much value from it? Because it's an OpEx, you can also end up, reducing the cost by sharing in a per pay-per-use model. And this is all through these examples, Citi, like Uber and AWS. That's essentially what they're doing, is they're taking these hardware assets and letting multiple people use the same thing as a way to reduce the cost. And because you don't own the hardware, you also end up worrying less about maintenance, right? Because you don't own the thing, you're just paying for the service. And because you're paying for the service and you're getting an SLA, problems often get fixed faster because it's now the provider's responsibility to maintain a certain level of quality. Similarly, there are advantages for the company itself offering the service. Like, it's not just a one-sided thing. Like with HaaS, like because you're converting CapEx and OpEx, it's easier to sell because it's a lower upfront cost, right? You're not requiring the company to make a big upfront investment. I'm not sure this resonates with you, but I could see that in your world, yeah, right? You're generating a monthly predictable revenue, which again is an advantage we've seen for years in the SaaS business, which is why everyone is becoming SaaS now. You get this here as well, where instead of having to sell the hardware to people, for example, the consumer world every holiday season, you can generate this monthly subscription, which again is easier to predict and easier to account for. Because it's ongoing, you're generating longer customer relationships. You're changing this transaction into a relationship. And number 4, look, hardware keeps getting cheaper and cheaper. Margin keeps getting squeezed. And what hardware as a service lets you do is kind of reframe your offering into value-based pricing as opposed to cost-based pricing. With value-based pricing, you can essentially attach the price you ask for to the value you're generating, as opposed to the cost of the actual thing, which is, I think, a losing battle. Put in other words, hardware as a service can be a shield against the endless march of hardware commoditization. Because as we know, as you're in a hardware business, your product is going to get cheaper and cheaper over time, and the question remains is, how do you maintain these high margins? This is one way, by tying it to value. Now, hardware as a service, again, it changes the relationship between the vendor and the customer. It takes this thing that used to be very transactional into an ongoing thing, which means, I think, as a customer, you probably want to be more, be more diligent about the company that you're embarking on this relationship with. But also, as a vendor, you have to pay more attention to existing customers, and you have to, which I think requires some effort, but I think the value will pay off. And I don't want to pretend this is an option for every IoT or hardware company. I think there's some companies where the sensors may be so cheap that they're disposable. I think you get this a lot with maybe small kind of tracking sensors or RFID sensors. I think in that model this wouldn't work. I think in other cases the hardware is just so expensive that you can't advertise it well, and you require some combination of upfront plus a monthly fee. But I think in general, I think this is very interesting. Any questions about hardware as a service before we move on to the third idea? Cool. Great. All right. Insight number 3, understand that IoT or machine data is really time series data. And this I'm going to get into this in a second, but this is, again, like, if you really want to really embrace this new world, I think this is a key insight. So here's an interesting graph. There's another interesting graph. And I think most people don't realize this, but last year was the first year that the number of connected machines on this planet, these are machines connected to the internet, not including smartphones and computers. These are things in the factories, things in the farm, this is your cars and your home. Last year was the first year they outnumbered us. And if you look at this graph, what's really interesting is that we're really good at producing new machines, but we're relatively pretty bad at producing new human beings. So we're already surrounded by these things, and the gap is just widening over time. And in particular, machines generate a lot more data than human beings do, in particular ones that collect data at, say, kilohertz. And they already outnumber us. So I think what's interesting is think about like the previous wave we were in, the big data wave, which came about in the 2000s, largely came about, the rise of Hadoop and Cassandra and Mongo. That wave largely came about because the rise of the internet. All of a sudden we had all this data that human beings are generating, like blogs and web pages and tweets and emails and pictures and text messages and whatever, and videos. and what we're finding now is machines generate more data than human beings do, and they already outnumber us. And so this new wave that's coming in, it's actually bigger than big data, which I think is, I don't know what you call that, but it's kind of this interesting notion. As a result of this trend, machine data is already emerging everywhere. We see it in our factories, right? As the gentleman over here in the front, our power plants, utilities are generating a lot of time series data. Our logistics and transportation world, this is time series and geospatial data. Even web and mobile eventing data, things coming from mobile phones, I think one could argue is machine data. And in fact, as we look to, I think, the future and in particular, space is a very interesting topic right now. There's actually a lot of time series data in space as we're discovering at Timescale as we work with the European Space Agency on one of their solar orbital missions. So it's emerging everywhere. So then that begs the question, what is machine data? And to explain this, I actually have a kind of a graphical example. Here we have machine data generated from three sources. We have a building, a farm, and a factory. And let's say these, say you have sensors collecting CO2, humidity, occupancy levels, temperature. And what these machines do is at a certain point in time, they collect all those data points and they record it, send up to the cloud, maybe where it gets written to a database. And then maybe a minute later, it records a new set of data points. And a minute after that is another set. And minute by minute, hour by hour, it's essentially collecting this sequential set of data, or in other words, a time series data set. And that's essentially the main idea, is that this IoT data and machine data is essentially this thing called time series data. Partly as a result of the rise of this new wave of computing, time series databases have actually emerged as the fastest growing category of databases in the past 24 months, which I think is pretty wild. And I've actually been looking at this graph every month for almost the last 2 years, and which I think we were like back here maybe. And this graph the trend is continuous. It's very much a real thing. And so you might ask, why do time series databases exist in general? And the answer is that existing databases actually don't work for IoT. But let me answer that in a different way, because this is actually a question we asked ourselves a year and a half ago or 2 years ago. The company that's now known as Timescale actually started off as an IoT platform. And when we were an IoT platform, we were collecting data from close to 100,000 devices. And it was all time series data, as you guys saw earlier. And so we're like, okay, great. There are all databases out there. We can just use one of them, take them off the shelf and plug it in, it'll work. And we actually tried a few, ended up using one in production for a few months. And we were just really unhappy with the state of the world. We felt like we were kind of stuck between two, we had a tough choice. Either we had, relational databases, which were reliable, which had a large ecosystem, were easy to use, were full SQL, but they were hard to scale, right? And on the other side, we had, NoSQL or non-relational databases, which scaled really well, so they solved that problem. But because they're relatively new, they underperformed on complex queries. They actually weren't as reliable. They didn't speak SQL, which meant that we had to learn a new query language and build new connectors. And in fact, because we couldn't store our relational data in those databases, they led to data silos where we had our time series data over here and then our device metadata over there. And then when our dashboards had to kind of display, say, uptime by device type, you had to do all this complex joining application layer. It just kind of sucked. And we're like, I wonder if we can do better. And in fact, at that point in time, every single time series database was a NoSQL database. And we were like, I wonder if we could do better and build a time series database that supported SQL at scale. And in particular, what we needed then was a database that was a time series database, was centered on time series data, but also allowed you to store relational data alongside the time series data, and also could support geospatial for our kind of use cases where you had a moving asset. But of course, because it's a database, all they need to be scalable, right? We needed it to be kind of perform kind of real time, give us low latency responses to complex queries, and also reliability, wasn't an option. We needed it to be reliable because this, for a lot of our customers, was their mission critical data, right? So the system didn't exist at the time, and being a group of engineers, we kind of built it for our own IoT platform. And over the next few months, we found that people were more interested. And actually, when we're an IoT platform, Santiago was there, and we actually gave a talk together at a Smart City event. And what was interesting is people were more interested in the people kept asking about the database and not the IoT platform. And after a while, people would say, "Oh, hey, like, can I use your time series database for like non-IoT data?" And we're like, "Yeah, just the time series database." And we heard this enough times that it got through like our thick skulls, and we realized that what the market really needed was a new kind of database. And so we ended up building it and launching it. So that's when we launched Timescale. We're a scalable time series database that supports full SQL. We launched 18 months ago. And now seeing quite a bit of growth and traction. We're packaged as a Postgres extension, which means to those of you who are familiar with Postgres, you'll know how to use Timescale. And we're open source, so it's an Apache 2 license. I'm going to just quickly talk about how Timescale works, but also I can go deeper in the Q&A if people have further questions. But at a high level, we support SQL for time series data. And SQL means that zero learning curve. So if you already know SQL, you know how to use Timescale. There's zero friction, so your existing tools like a Tableau or a Grafana or Power BI or Kafka or Spark just work out of the box with Timescale. Because we support relational data alongside your time series data, you can enrich your data. You can enrich your time series with relational data at query time. In terms of scale and performance, and I'll have some more graphs in a minute, we scaled to millions of data points of writes per second, scaled 100 billions of rows on a single node, and as I'll show in a minute, we're faster than some pretty major databases for time series data. But at the same time, we're scalable and we're new, but because we're built on top of Postgres, we're already enterprise ready. We inherit 20 plus years of Postgres reliability. We support their entire ecosystem for stream replication and backup and admin tools. And we already also support enterprise-grade security. One of our production deployments includes Cray, the supercomputing company, who've been using Timescale for over a year to store all kinds of sensor and telemetry data. They've scaled to 500 billion rows, so 500 billion rows, while sustaining 400,000 inserts a second. And at this interval, they actually have quite a few partitions. And they have 70% faster queries. And I think what was really interesting about this is that, especially within the context of IoT, is you get such a heterogeneity of deployments. Like we're deployed on the edge on like Raspberry Pis, but also deployed for essentially device monitoring workloads on a $10 million Cray. So I think it's pretty cool. In terms of performance versus a relational database like Postgres, we're actually 20x higher inserts at scale. Anywhere from just as fast to hundreds to 1,000 times faster on certain types of queries, especially time-ordered queries, and we're 2,000 times faster on deletes. But even versus non-relational system NoSQL databases that are known to be scalable, we actually perform quite well. We're 20% higher inserts versus Mongo, but a lot faster on queries, like again, hundreds to thousands times faster. Versus something like Cassandra, we actually see 10x higher insert performance, and again, thousands times faster queries for time series data. And in fact, with Cassandra, we run this experiment that even surprised us, where we had a 3-node cluster of Timescale outperforming a 30-node Cassandra cluster for 1/10 the cost, but with the same kind of HA and replication guarantees. So that was pretty cool. Versus Influx, which is a popular time series database. One of the biggest differences is that we fully embrace SQL while they're going in the opposite direction towards their own custom query language. There are also quite a few other differences that I think are hard to cover in one slide, but we have a blog post that talks about it that I can share with folks later. Question? I don't think we've had it's wherever Postgres runs. I'm not sure if Postgres runs on ARM yet. Does anyone know? I can look that up later. Yeah. I don't think so. Right? Yeah. So the question is like, okay, like you guys are like a relatively new database. There's all these other databases that are out there, and you say you're much better. Like how? Like what's the catch? And there's no catch, but there is an insight, and the insight is that time series workloads, which is what you mainly see in this world of machine data or IoT, if you will, are different than what traditional databases are used to, right? You think about the traditional database, which some people think of OLTP or a transactional workload. So here's an example, right? So let's say you have a bank, right? And you're a bank and you're keeping track of someone's bank account, right? The traditional OLTP workload is I send Santiago $10, find my bank account, find his bank account, which might be randomly in our database, and in one atomic transaction, debit my account and credit his account. So what you're seeing is you're seeing primarily updates, right? You're seeing writes that are randomly distributed across random keys because you don't know where like my bank account is, where your bank account might be, and transactions to multiple primary keys. Time series is actually quite different. Where if you remember a machine data example, you're primarily inserting data, right? You're primarily inserting to the most recent time interval. You may have something that are slightly out of order, but they're generally recent, and your inserts are primarily associated with a timestamp. So that's insight number one. Insight two is we also, we actually like did some research into why relational databases are hard to scale. And here's a quick graph. It was actually plotting insert performance on the y-axis versus the data set on the x. And as data set grows, what you find is insert performance just essentially falls off a cliff and becomes more variable. Do people know what's going on here? What's going on? Any ideas?
As far as database goes?
Yeah, like why are you seeing this cliff? Or any thoughts, maybe?
I think it's just a matter of that whenever Postgres queries something, it'll run a query against every row. And
Yep.
if it needs to scale, it has to do those things
Yep.
against every single row for every single calculation.
Yep.
And it just doesn't scale.
It's very close to that. Very close, yeah.
Index updates?
Yes, but why are index updates fine over here? What's that? It's smaller. Yeah, so it's the size. So what happens here is, so what you're essentially seeing is a trade-off between memory and disk, right? So what you find here is all your data and all your indexes fit inside working memory. But after a while, you essentially run out of memory and end up swapping to disk. You get this data set super large, and you end up swapping random parts of your, random pages and parts of your treated disk. And as a result, you get this thrashing motion. Now, of course, you could invest in more memory, but you're just pushing this graph out for a cost. But it turns out you can do better. And here's how we do better. So here's how timescale works. So if you remember our image from before, you have this sequential set of data, so time series data coming in from our machine data sources. Our first insight is that you can essentially partition this data by time, right? You can say, okay, maybe this is today, yesterday, the day before, and you can kind of configure that, right? The second insight is you can also partition by any other dimension, right? That we call space, and within a machine data context, it might be the machine data, device ID. In fact, in Timescale, we support any number of space partitions, but again, what you end up having is these n-dimensional chunks, and what we end up doing is ensuring that each of these chunks, which are stored as a Postgres table in itself, are small enough such that you can have a few of them fit inside memory. So what we end up doing is creating these smaller partitions such that you can have your hot partitions in memory and your cold ones on disk, and you avoid that thrashing. Now that's like insight number one. But insight two is, even though your data is heavily partitioned, you don't want to have to worry about creating new partitions on the fly, and that's what we do. Is as your data comes in, we'll automatically route the new row to the appropriate partition and create new ones as necessary. So you don't have to worry about partition management. But inside three is you don't have to worry about the partitions at all, because what we end up doing is we end up hiding all these chunks behind this abstraction there that we call the hypertable. That gives you the illusion of a single table across all of your data. So you may end up having, in the case of Cray, like 50,000 partitions, but it looks like all your data is in one table. And in fact, this looks just like a Postgres table, such that creating indexes, creating triggers, constraints, foreign keys, upserts, table management, creating schemas, maintaining schemas, are the same for a hypertable that they would be for a vanilla Postgres table. And in fact, because it looks just like Postgres, in fact, getting started is really easy. What you end up doing, for those of you in the room who are familiar with Postgres, you just end up creating like a normal Postgres table with a schema. You end up converting it to a hypertable that takes a minimum of 2 arguments, which is the name of the table that you want to convert to a hypertable and the time column in that table. And then you just insert into it, as if it was a normal Postgres table. Pretty easy. And one more thing I want to add before I close out is, the reason we built Timescale, and I think the reason why it's useful and we found it useful for our own IoT platform, wasn't just performance. There's actually quite a few other reasons. One is it actually allowed us to simplify our stack. So you remember in the IoT example, IoT platform, we had our sensor device data over here and our metadata over here. We had these silos that we had to join at the application. It actually led to really some really complex application logic, which also meant that if we had to kind of modify the join, we had to kind of push out some new application logic. With Timescale, we can simplify our stack and then keep our relational data with our device data in one database and do the join with a SQL join at the query level. Another advantage is we actually also extend SQL for time series analytics. And this is actually examples looking at, I think, some cryptocurrency data. And it actually highlights a couple of functions that we added, which you can read about in the docs, but essentially it kind of extends SQL for time series analysis. We play well with other Postgres extensions, including PostGIS, which means you can now use Timescale with PostGIS for geospatial temporal data, which is actually one of the use cases that a major financial institution is using us for. Another advantage is you can have data retention policies and with different aggregation levels. So you may decide to keep data at different granularities for different periods of time, where maybe the raw data just for a week, but maybe you keep the daily data forever, which I think you often find in use cases where you have a lot of kind of raw data. We play well with some monitoring tools, so we also allow you to unlock the richness of your monitoring data. We've built native connectors to Prometheus, and we have a native support that's shipping in the next version of Grafana, which is currently in beta. I think comes out in 2 weeks. And as a result, you can end up using Timescale for monitoring purposes. This is actually one use case where Comcast is using us for, where they're using Timescale in combination with Grafana to monitor metrics for their 120 petabyte data center, which seems very large to me, but apparently it's very small for Comcast, but it's cool, and they're very happy with the performance. I think one thing that was really interesting about this was that one of the reasons why Comcast ended up using Timescale, was the ability to actually expose a SQL interface to power executive dashboards in Tableau, which is something that a NoSQL database could not do. There's more about PG Prometheus, which is how we connect to Prometheus. That's on our docs. You can look it up. And here's a quick demo of the kind of Grafana kind of native query builder that lets you build SQL queries through a graphical interface in their application. If you want to learn more about this, one of our colleagues is actually giving a talk this Thursday at the Time Series Data Meetup at Two Sigma Ventures Thursday evening this week. Obviously, we have a roadmap. We're not just stopping here. We're a lot more in the pipeline around kind of scalability, performance, ease of use, and also reducing total cost of ownership. But yeah, that's Timescale. So in summary, as we think about this next wave of computing and IoT, I'd really like to push you guys to think about 3 ideas. And the first idea, again, is that there is no IoT, but your business is changing. And I think this is kind of forcing us to use a more specific language to what we're doing than marketing speak, right? Insight 2 is to think about some new business models that IoT enables, and in particular the hardware as a service subscription model. And number 3 is understand the role that data, and in particular time series data, plays in IoT. Also, if you want to learn more about Timescale, you go to our website at timescale.com. We're an open source Apache 2 database. You can find us on GitHub. And we also have a pretty active community on Slack that you can feel free to join. So yeah, that's it. Thank you. Any questions? Yes. And I'll make sure I'll repeat the question. Yeah.
So we talked about using inserts to create time series data.
Yep.
In terms of production of data, I think that makes sense.
Yep.
When it comes to consuming the data, you talked about consuming the example through Tableau.
Yep.
You also talked about consuming at a higher level by aggregating maybe a weekly bucket, whatever.
Yep.
So what are different ways of consuming the data from the time series database?
Yep. That's a great question. It reminds me there's a slide that I should have added to this presentation. So Timescale looks just like Postgres to the outside world. I'm sorry, you're right. Totally forgot. The question is, I talked about a few ways to write data into Timescale. What are the different ways to consume data out of Timescale? Cool. Number one is obviously you can query the database using full SQL. Number two is we look just like Postgres to the outside world, which means that any tool that talks to Postgres will work with Timescale like 99% out of the box. So like a Tableau that talks to Postgres, you can use Tableau, you can use Grafana. We did some custom work to make it even better for Grafana, but Grafana works. Any of the libraries that might exist in like R or Python or Go will work out of the box. A lot of the common ORMs, like what you find in Rails and SQL Alchemy, will work. Some of the modern solutions like Zabbix that work with Postgres will work with Timescale. So there are quite a few ways, and I think to answer your question, it's really anything that talks to SQL plus a few other things that we've added like Prometheus and Grafana. Cool. Other question? Yes, please.
If you have a query that, God forbid, hits every partition of your hypertable, what's the overhead like over just Postgres in that scenario?
So that's a great question. So the question is, if we have a query that hits every partition in the hypertable, what's the overhead look like? So it's not good, and that's not the use case that we're optimized for. So it's a totally valid question. I'm going to answer your question in two ways. So first is, it depends on how, and your resources, blah, blah, blah. But in general, we will be slower than Postgres on that query because, querying, let's say 100 chunks will be slower than one table, right? Today, what we're working on is better kind of query parallelization such that we can actually distribute the query and almost do like a map reduce type thing on the database. That's something we're working towards. But the main thing the main workloads we focus on today is that if your queries are mainly going to touch like a few chunks because they're time bound, then we're great at that. But if you're going to end up doing a lot of kind of data science-y like queries where you're going to touch everything because you can't rely on time, we're actually not. I wouldn't recommend Timescale for that today. Cool. Other questions?
Cool question.
Yes, please.
So like in that Comcast use case, you're dealing with a lot of streaming data, right? And my question is basically instead of sort of going, let's say, with something like a Kinesis to a DynamoDB, can you go directly into, let's say, TimescaleDB?
So the question is, can you connect, instead of connecting through, for example, AWS has a product called Kinesis, which is a message bus product, which connects to Dynamo, which is one of their NoSQL non-relational stores. Can you connect to us? I believe Kinesis works with RDS out of the box. I think with some work you can get it to talk to your own Postgres instance. So you can connect, I'm pretty sure you can connect Kinesis to Timescale because it looks like Postgres. But you can also just use Kafka instead of Kinesis, if you don't, which you may want if you don't want to be tied to a certain cloud provider. And in Kafka and Timescale work very well out of the box. Another question. Yes, please.
You do something if you want to report on time series data, put it somewhere else, so you could look across, all the way back in time, what kind of things would you do for that?
I'm sorry.
So
Yeah.
You were talking about it's optimized to look at the most recent data, or across different slices of data. So maybe you're looking what happened 3 months ago on some floor, and you're looking across all the devices at that moment. So that's to optimize the things you're doing about before. But you might want to report on things where you're just going back through history.
Yep. Okay, so the question is, if you want to go back through history, how do we support that? We support that in a couple ways. Number one, Timescale, the way we're architected, we actually make it really easy to elastically add disks to a machine. And so what one can do is, as you're collecting data, you can dynamically add storage capacity to store more and more data. So you may choose to say, I want to store all this data, right? So I want to store all the red data for the past year, and I will attach 50 terabytes or 100 terabytes to do it. That's option one, right? Option two is you may say, hey, my raw data is actually way bigger than that, so I can't do that. But I'm going to downsample it to hourly or daily or something, and we keep that data. So that's another option. A third thing you might do is actually export your old data to a kind of a data warehouse or data lake, like an S3 or an HDFS, where you say, hey, I want my hot data here and my cold data in a kind of a traditional data warehouse. in which case you're almost like using timescales as a front end. Right now, if you wanted to query both timescale and your data warehouse, you'd have to join that at the application layer. But one thing we have in our pipeline is actually allowing timescale to be the front end for the whole thing. I think those are the three options. Yeah, cool. Question in the back. Questions are we on AWS? The answer is today you can deploy it yourself on a VM. Soon we will have a managed version of timescale, and soon we'll have a managed version of timescale that will run AWS. Set up.
Your company is built on AWS.
So we're a database company. So we essentially
A data center?
So we're a database company. So we write software and we distribute the software. Today, some people choose to run that software on the edge on like a $5 Raspberry Pi, or on like a $1,000 gateway, or like a $10 million Cray, the full spectrum, right? Some people choose to run the database in the cloud, and the cloud might be their own private data center. It might be the public cloud. It might be some hybrid option. We supply that full spectrum of deployments. We're agnostic. We will help you in your deployment. For certain companies, we will help manage.
You could be on Google.
What's that? What's that?
Google's going to be in town on Thursday. And you can be on Google. You can be on.
We could be. Google's me on. I guess Google's me in town Thursday. Yeah. So yeah, we can be. Yes. So you can deploy us today on any of the major cloud providers, and fairly soon we'll have a managed offering, so you can deploy it through like a couple clicks and not have to worry about managing it. Yeah. Pretty soon. Yes.
Are the Postgres like core maintainer people expressing any interest in pulling this stuff in?
Yes. So the question is, are the Postgres core maintainer people expressing interest in pulling this stuff in? I actually think so. Not as much as you would think, and the reason isn't because they don't find this useful. It's because the Postgres roadmap gets set so far in advance, and we're moving so quickly. There's just a mismatch in, this is another reason why we have to be a separate company. We can't just send everything upstream. Is like there are features that are going to Postgres 11 this fall that were submitted as patches like 14 months ago, But that makes sense. If you're maintaining Postgres, you need to be that careful. I think, but for us, we're a startup, and I think our users expect us and want us to iterate quickly, which is what we're doing. I think over time you'll find that some of the things we develop, we'll just submit upstream. And there'll be some diplomacy that we do to do that. But I think some things just won't make sense because some of our optimizations are specifically for time series workloads, while Postgres is designed for OLTP. Yeah.
How do you coordinate things like binary data, video, and audio? So you've got cameras on something, you've got all sorts of sensors that are around whatever you're filming.
Yep.
And odds are you want to kind of look at it at a given moment. So usually you just put large files and go back in time and use time to scroll through the binary.
So the question is, if one had a lot of binary data, how would one associate that within timescale? And there are really two ways. One is, depending on the size of your binary data, you can actually store it in the row. Postgres has this there's a binary data type, there's a JSON data type, there's a JSON B data type, which I think is somewhere in between. You can also, what some people do is they end up storing like a pointer to a file or through an S3 bucket. But yeah, obviously there are different trade-offs for that. I think we've run out of time. So if folks have more questions, I'll stick around. But thank you so much for coming. And thanks, yeah.
There's 3 more bottles of beer. So.
Pizza left over there.
There might be some pizza as well. Thank you for coming. Yes. Oh, what's up? Yeah. Why don't you come up?